When I introduce the topic of electricity for the electricity units in my grade 9 class, I always start with static electricity. There's always a good points to do with the fact that we have particles, negative particles that can be controlled, move from one place to another. And from there, we can either play in class, learn that electrons exist even though we don't see them. We can actually have them move, and what else we can do from there. So here, this is my favorite cat that I bring along in my class when we look at static electricity. So when you have static electricity, what are you thinking about? So some people will say, well, if you think of a balloon, we know that if you inflate a balloon, let's see if I can inflate it for you. Very good. We're going to do a knot. We know for the most part, if you have a balloon like this and that you're putting on your hair like this, if you're lucky, it might be able to be attracted to an object. Let's see what I have here. So it's not attracted to this one. Sometimes you can put it on a wall and it's not going anywhere. There you go. But you most likely have seen this idea that if you rub your balloon on your hair, you have static electricity. Actually, you can see some of the hair are being attracted right now from the balloon. So what is going on here? So let's have a look. When we think of static electricity, we have to think that there are particles in matter. So what do I mean by particles? If you take a piece like this brush right here, and then you were to cut it in half, and then cut it in half, then cut it in half, at some point you will end up with only one particle of plastic. Now, we also know that if you have matter, matter is made of, let's say I take an atom. So let's take something, if you think, how can I say? Let's say an atom of zinc. In the nucleus, you have positive charges. You have also neutrons that have zero charges. And you also know that we have electrons that are negative that are orbiting around these. So I'm not going to do the whole particle here, but it's just to say that we have here usually the same number of positive than negative. Because if you have positive charges plus negative charges, the plan is always to aim at neutrality. If you have 5 positive charges, you have 5 negative charges, and it makes it neutral. Now, what's interesting is that if you give energy to matter, electrons on the outer shell here, electrons that are within the matter, can move around a little bit. So here's how. So if you have your hands and you rub them like this, you will notice that you can feel some heat between your hands. This is from friction. You're creating heat, and heat is energy. So when you do that, what happens is that electrons get excited and they are moving from one place to another. So if you take the balloon right here and you rub on your hair, you have friction. Now you have a charge that is created. So electrons have moved from one material to another. The big question is, from which way did it go? Are the electrons from the balloon to your hair or from your hair to your balloon? So that's a good question. So we have what we call the triboelectric series. So triboelectric series is a list, or they create lists of materials. And the list of materials, where is it? Right here. Oh, it keeps getting smaller. Interesting. Let's see, where is it? Perfect. So there are a list of materials. So if you look here, let's see if I can make it a little bit bigger. You have here at the top glass, mica. You also have fur. So in the fur part, you can think of animal fur, going back to my little cat right here. And you can also consider human hair. Very similar in composition. So here we have in the positive end of this triboelectric series. Why would it be positive? That means that if you give energy through friction, we have here electrons in our hair. They'll be more than happy to jump off somewhere that wants those more strongly. So if you go down here the list, we have cotton, we have amber, wood, we have copper, silver, and gold, because we have metals on these. You end up here at the bottom with different materials. So here I have natural rubber. And if you think of a balloon is made of rubber, synthetic rubber here. But if you rub on your hair, so let's see if I can make it bigger. If you rub on your hair, what happens is that you have friction. We have electrons from hair that are held like weakly, and we have here a material that is rubber that are attracting strongly electrons. So when you rub, what happens is that you end up with electrons moving from your hair to your balloon, and therefore, if negative electrons are leaving, you end up with, let's see, electrons are moving away, you end up with, let's say, 5 positive with 3 negative, and that creates something that is, that has a positive charge. Look at this. My face is gone from the screen. So you end up with an overall positive charge, which is what I have here. However, if I have on the balloon at the beginning 5 positive and 5 negative, and on the rubber they attract the electrons that have been moved, what will happen? Now you end up with 7 electrons, and the overall charge, or the net charge, is now 2 negative, and therefore we have a balloon that is now negative as a charge. So here what's interesting, we have 2 laws, the laws of attraction and the laws of repulsion when you think of charges. So you have, when you have 2 positive charges or 2 negative charges, what do? They want to repel each other. Because they have the same charge, they don't want to be side by side. So this is what we call the law of attraction. So law of attraction. Now we also have a situation where we have negative matter and positive matter, or negative and neutral, or positive and neutral. And if you have them, what it is, we have what we call, oh, look at this, I made the wrong one. So this is what we call the law of attraction down here, because you have opposite charge. So I made a mistake here. What do I have here if we have the same charges that repel each other? This is, it happens. We have the law of repulsion. If it happened that you picked up on the mistake, please put at the bottom here that you're happy that I found the mistake on the board. So here we have objects that have different charges that get together, that are attracted to each other, and we have similar charges that are repelled from each other. So what's interesting here is that if you have an object that is neutral and your hair that is neutral, you create some friction. You have your hair. Let's see if I can go back here. We have here human hair that are attracting weakly electrons. So electrons attracted weakly will go to the balloon, which attracts strongly. Here we have that rubber. They attract the electrons. So when I distance both of them, this is now negative, my hair is positive. If you put them close by, my hair will be attracted to the balloon. If I take the balloon and put it on a neutral wall, when I have the great, when it works, the balloon stays on the wall. So here, this is an example of static electricity. Now, it is possible that some matter will attract more and more and more electrons, and what's interesting is that electrons can accumulate in areas that contains water. What's interesting, water, if it is in the atmosphere, can accumulate electrons or negative charges very easily. Now, some of you would say, okay, how come it's only the electrons that are moving? That's a good question. Now you have to think that when you have, let's say, an atom, let's see if I can put it big again. When you have, let's say, an atom with positive charges in the middle, and the positive charges are called protons, and they are surrounded by negatively charged particles, which are electrons, the mass of those two particles are quite different. Because if you take the mass of one proton, like this, it is about the same, plus or minus 100, of about the mass of 2,000 electrons. So here, the mass is quite different. So in my class, I often give the example, if you think of the athlete, the sumo wrestlers, and then you have little kids that are 3 and 4 years old that are running around. If you have a sumo wrestler that are sitting on the ground, the little kids that will go, they will just bounce back on the sumo wrestler because the mass of the sumo wrestler is so much bigger than the little kids. And therefore, if they run, they will just bounce on an object that is much bigger. And it is, in this example, the sumo wrestler. So here, the electrons being so much smaller, being so much lighter, when you create friction with your fingers, with your hands like this, only electrons are moving, which is good because if you are rubbing your hands like this, your hands are not melting, you're not destroying your cells in as a body. If you have a balloon and I go something like this, the balloon is not changing shape or exploding. And the reason for that is that matter is still self-contained, which includes the protons and the electrons, and only a few of the electrons will be moving without changing how matter is. Okay, so this is the first thing here, which is good. So let's go back to my image of the clouds. So if you have a cloud here, often you see that at the bottom it is flat. And the reason for that is that if you have a cloud that goes from east to west, but you have wind going from west to east, you have friction between air that is lower and the clouds above. And what's interesting is that air, it tends to give electrons if it has any. And at the top here, you have clouds. And in the clouds, there's a lot of water droplets. And what that means is that it attracts electrons. So as the cloud is moving with the wind and electrons are accumulating, you have the bottom part here that can be negative. And because there's so many more electrons here, the top of the cloud may appear more positive, even though it's neutral. Or you may have, when you have very thick clouds, you have crystallized water. So here often ice crystals tend to give electrons so much more than water droplets. So it's creating changes in the clouds. There you go. And that's why sometimes if you are at night, you can see within clouds, when it's a big thunderstorm, you can see lightning within the clouds, because you have here the electrons at the bottom part of the clouds that want to neutralize itself, and they're attracted to the positive of the top of the cloud right here. Now that brings us to the idea as why is it that when there's a thunderstorm and you can see lightning, you really want to go inside your house. You don't want to be standing by yourself in a field. Oh, I cannot make this bigger. That's okay. Oh, very good. There you go. So here, if you have a field and you have a tree like this, but you have at the top a cloud that has more electrons, what happens here is that the electrons at the top will influence the electrons at the surface of the ground to go a bit deeper in the ground. And the reason for that is that the electrons here, which are negative, considering the law of repulsion, will push down the electrons here. So you have the ground that is more positive. If it's flat, it's nothing to worry about. However, if it happens you're in the field and there's one tree, let's see if I can show it here. You have the one tree here. What happens is that the electrons in the clouds are influencing the electrons to go a bit further down, but that means that the head here of the tree is now more positive than its roots. So if you were to have a human right here, you would have the head of the human much more positive than its legs. And what happens is that you always have extra electrons in the atmosphere because they're trying to find a way to escape from each other, because all these electrons don't like to be close to each other. So and sometimes if you have a lightning storm, you can feel the static electricity in the air. For some people, they can actually feel it. So what happens? You've got a few electrons that are escaping. And once they find a route, what will happen here is that the electron will say, oh, we have our outing, and they will follow the lightning towards the tree here. This is an example of what we call grounding. It's taking the surplus of electrons and going into the ground. If it is a tree, it is sad for the tree because as the wood is an insulator, they tend to be breaking down due to lightning. Now, if it happens that you have a human right here, it will be the same thing. The lightning could go to the head of the person, and it will be very sad news for that person. Because keep in mind that we have our brains that are sending micro, let's say, very tiny, how do we say that? Influx of electricity to go from the brain to your heart to make it beat. So there's a lot more electrons here. So a few things. It can get burned, the heart can stop beating, and it's very dangerous. If you're lucky, there's not too much. You may have a burn and your heart will start beating again, but it is something that we don't want to happen to you. So this is an example of grounding of the charges. Now, some examples that can arise from that could be interesting. So I went on Amazon and I look at something that is called an electrostatic paint. Let's see, do I have a good one? It's electrostatic power sprayer. So it's done for paint. There you go. Electrostatic powder coating machined paint gun. So here we have a paint, a machine that gives paint, but we're putting charges to the droplets of paint or the particle of paint that we want to put on an object. So let's see how it works. Perfect. So if you have something that you want to have particles sprayed on a piece of paper or on a piece of metal, what happens here is that if you are sending particles away, you end up with a fan of particles going on the object right here. Now, what is better is here, if you are looking at an object like this, if you can have an electrostatic let's see, spray paint machine, you can actually put charges on the particles, and when it reaches the object, you can actually find a way to neutralize the object through the paint particles, and let's see what it means. So here, when you have let's see if I can get color. Let's get orange. So you have particles that are going everywhere. And what happens is that you have paint particles that will go here on the edge, but here it will just fill out and it becomes a coat of paint if there's no electrostatic forces. Where if there is electrostatic forces, what happens, there's a few things that are interesting, is that when the paint droplets are coming here, it's not just going on the top here, but it's actually attracted to the object because we put a negative charge to the paint droplets or for the powder. When it goes to the object, it's actually attracted through the electrostatic difference in charges. So a positive charge and a negative charge. So what happened here is that you have paint is actually going, when it goes on a surface, it will actually go and want to be as close as possible. And that's why when you have a new car, the paint work on the new cars is so much better and they're so much more durable. Now, as soon as there's a puck or there's something on the body of the car, what happened here is that there's a nick in the paint. And if you paint over it, you're just putting drops of paint on the surface and it's no longer attracted. And that's how paint that comes after an accident, or you have putty to block a hole, the paint job that you do after an accident when you redo the work is never as good as the original paint on the car. Because when it's done with electrostatic, we have the paint that is going exactly where you want to go. And if it happens you have a particle that goes past it, what happened here is that you can have an attraction. So here the negative particles is attracted here, and here the particle is attracted there. And there's a beauty for that, because there's a decrease in the cost of paint if you are to ever use electrostatic paint devices. And the other one here is increases safety of the people. Because if you are looking at an example here we had earlier, if we have here the paint that is focused on one area, and here you could see, I'm sure there's a vent and there's a filter here to make sure things are good, but you don't see yellow all outside, and you don't see yellow on the human right here. Whereas if you have here just something that will go straight on an object right here, the issue is that you end up with particles in the atmosphere, and it's not good for the worker's lungs in that case. So all of these are important in that example. And let's see if I have another example for you. The other example I had for you was, let's see, there's a paint, and that's all I can think of. I forgot the other one. It happens. So when you think of static electricity, we can just say, well, we can play with static electricity. We have a balloon like this. If we want to apply it, then there's a way to actually focus the charges using electricity. So we can have objects that are positive and objects that are negative. And when we start putting some circuits, you can actually use metals, where if you have aluminum tends to be a bit more positive, or gives away its electrons more easily. And we have, for example, copper that likes to have the electrons a little bit more, in which case we can actually get charges with metals in circuits, and then we can have a good fun with a spray gun like this, or a piece of equipment that could use static electricity. So this is the information. I feel like my mind was all over the place to give the example. Hopefully you have appreciated this example. And on this, I'm going to put a link to a video here related to science, and I'll see you there.